So again, we're going to focus on the letter t. That's the variable in question. I'm going to treat everything else like it's a constant. And the first thing I'm going to do is I'm going to look at the first term, the t cubed. I'm going to grab its exponent, 3, and I'm going to multiply that first term by 3. But before I finish, I'm going to take 1 away from the exponent. So 3 times t to the 3 minus 1, or 2. So the first term becomes 3t squared. And that's literally it. There are a few little things that have to be taken into consideration, but that's ultimately all you have to do. And now you apply, again, this to each of the other terms. So put a minus sign because there's a minus sign next. I'm going to look at t. It's to the squared power, so 2. I'm going to take the 2 down and multiply it times the 4. Then I'll bring the t down and subtract 1 from its exponent. So t to the 2 minus 1 is just t to the 1. Last, 3t is 3t to the 1 power. So for the last one, 3 times 1 is 3. But then, although I could write the t here, it's t to the 1 minus 1, which is t to the 0 power, which means just 3. I'm assuming that most of us had no real difficulty with that. The next part, of course, is just to do this again. Acceleration is the derivative of the velocity with respect to time. So I'm going to repeat this process. And I'm not going to write this out. I think we can skip that part. I'm going to take the 2, multiply by the 3, and get 6t to the 2 minus 1, which is just t. Next one, the exponent's 1. So 1 times 8 is 8. T to the 1 minus 1, or t to the 0, so it's just 8. Now, here's something new. The 3 doesn't have a t in it at all. We can put a t to the 0 there if you like. It just means you're going to bring a 0 out front and multiply the whole thing by 0. But also, I'd rather you rationalize the idea that does the 3 change with respect to time? The answer is no. This whole thing is about finding how the variable changes with respect to time. And since 3 is a constant, it doesn't change with respect to time. It becomes 0. Or essentially, we lose the constant. Now, that's finding the functions, starting with the position and using the derivative to find the other functions. Any questions about that? I assume that part really isn't the challenge. There might be other challenges here, but that shouldn't be it. If you've never done it before, it takes practice, which is why it's been posted, practice. Now, you were asked to do other things, and this is where I really want to make sure that you understand the nature of what you've done. But this, you don't need to know what we've just talked about to do question 1 and 2, but you do have to have the functions. Question 1 and 2 is just making sure you know that these 3 functions work together. So if I want to find out how fast does the object pass through the origin, I need to know when it's at the origin. These things are all connected by time. So to figure out when it's at the origin, I set the position vector equal to 0. When its position is 0, it's at the origin. So I suspect you can find the roots of this value, or this function. I've chosen one that will factor. And on any test, I'll try and focus to make sure they factor, but you don't have to factor this. You can use other methods to figure out what the zeros are. So you should have a few methods at your disposal, but you guys are just starting pre-calc. Your methods might be limited. But you guys who have finished pre-calc, you should have, 2 or 3 different methods for doing this. But it factors. And so anything like this I'd provide you with, it will factor. And so the first factor is t. It's going to leave me with t squared minus 4t plus 3. So that's going to be a 3 and a 1, based on the fact that it's positive 3 and negative 4. Both of these are minus, and those represent my 3 factors. So there are 3 times when the object passes through the origin. It passes through the origin at t equals 0, t equals 1, and t equals 3. This is not the answer. The answer is for you to figure out how fast it passes through the origin. So you now have to do the velocity at time 0, the velocity at time 1, and the velocity at time 3. I'm assuming I don't have to really do that you can plug in a number and calculate it. It's the least important thing here. But if I have to do some of this, I will. Is there anybody who needs to see me to perform this? Oh, good, because I don't want to. So what is the object's position when the acceleration is 0? Same idea. Set the acceleration equal to 0. T is 4/3. Go back and plug that in. This time you're plugging it into the position function. It's not going to be pretty. 4/3 cubed minus 4 times 4/3 squared plus 3 times 4/3. It's probably going to be a mess. You can do it all as a fraction if you want. I don't really care. You can give me a decimal. It makes no difference. This is an exercise. The number is really not that important. Any questions about this? This is review from yesterday. All right. Well, the expectation is that you should be able to do a little more than this. What I really want you to do is I want you to work from any one of these relationships to produce the others. I don't want to always assume we're going to be given something about position where we can take the derivative. In fact, we probably won't. We will more likely be provided with something about acceleration and be asked to figure out velocity and position. So I need you to be able to work in both directions. I should be able to give you any one of these functions, and you should be able to create the other 2 functions. So I'd like you to consider this function. And I'd also like you to know that at time 0, the object is at the position -12. Now, for those of you who know why I gave you that position, good, hold on to that. For those of you who don't, you'll see. Now, I would like you to figure both of these out. So let's see if you can do it. Can you do the thing backwards? I'll give you a moment, but I'm just wanting to know if you can. You'll know if you've gotten it right, because when you take the derivative, it should give you back where you started. So try it out. See what happens. I feel like I need to be at least a little bit thorough. Let me just make sure. Okay, should have gotten, and I saw it on almost every paper, is t cubed minus 18t squared plus 96t. But here's where I have to stop you and remind you that if there was a constant here, it would have disappeared in the process of the derivative. When you take the antiderivative, when you work backwards, we have to leave something here to indicate that there might have been a constant there. Now, in calculus, you'll probably just put a nondescript thing here, like a c for constant. In fact, they'll probably do something completely different than that if they're doing indefinite integrals differently than this. For me, however, this has meaning. This is the location of the object at time 0. So we know to express that. We have a name for it, and that's the initial position. There's no way to know the initial position unless they give us some other context. I gave you context. I told you the initial position was -12. You could have put the -12 there and that would have been fine. But also, be aware of this. They could have said, well, the position at 12 seconds is negative 47. And ask you to figure out what the initial position is. So they don't have to give you the easy road. They can give you a crappy road, and you have to work it out. Do you understand what you have to do here? You put in 12 for all of those, put negative 47 in there for the function, and solve for x naught. We don't do this particularly often in my class, but luckily calculus will hammer you with it, so you'll get lots of chances to do it in calculus. So knock yourselves out over there. But we're not going to do anything like that. We generally have the initial condition. I will call this the initial conditions, but sometimes I will break form, and instead of calling it initial condition, you'll hear me say something else. I will often call it the boundary condition. It's an old habit. So if I slip into the old way to describe things and say boundary conditions, I mean initial conditions. You can take the derivative here, 6t minus 36, and now we could talk about different problems if you'd like. I made the velocity factorable, so I could say where is the object when the velocity is 0, or I could say how fast is it going when the acceleration is 0. I mean, any one of those things if you want. I don't think we need to practice the algebra. I think we need to focus on the calculus. Okay? But if you would you like some other practice questions like that? Do you want to do one here in class? Want me to give you something like that? Or can we kind of move on to something else? My expectation is this is not particularly hard, but some people need more practice than others. Third period did not need much more practice. So we moved on. Are we good to move on? For all of you who are practiced at this and have already had calculus, let's have a quick chat. You guys who are, this is new to, well, you should listen, but understand that I'm trying to make sure I give everybody in the room a little bit of value for being here today. And I would like to give a little bit of value for them real quick. It shouldn't be a surprise to you that this can be written as dx dt at any time. And for all of you, that has to be true. If you see dx dt, they mean velocity. And the acceleration is dv dt. But that is the derivative of a derivative. We can substitute in there for v dx dt, which means this can be written as d dt of dx dt. So this is a way of writing the second derivative, and we have a shorthand for it. And shorthand, I mean it's not short, it's a mess. But the second derivative takes the two d's and acts like you're squaring them. So you'll get d squared x, and the bottom is dt times dt, so they'll just put dt squared. And they'll use this as the symbol for the second derivative with respect to time. Now, if you've never seen that before and you've never had calculus, good, it's good to see it. It's appropriate to understand, though, that that is simply a way of writing in longhand that you're dealing with the second derivative. When you go to college, they don't do this. And this is something that I think everybody should pay close attention to. Even though it won't be an issue in my class, it shows up. There's shorthand for all of this, ways of writing this that's neater. You guys in calculus have already done things like this. Using a prime notation to indicate the derivative. The issue with prime notation is that it is a generic notation for the derivative. It's suggesting here that we are taking the derivative of some function that is a function of x with respect to x. That's what the f prime means. So these two derivatives here assume that the derivative is taken with respect to x and that your function is related to x. That functional notation is okay. We don't use it much in here because our functions have meaning. This function is position. So I guess I could write this as x prime of t if I wanted to. But in most engineering and in upper division physics classes, they use a different notation entirely. They put a dot over the top of the variable, The dot is a very specific meaning. It's not any derivative. It is a derivative with respect to t. X dot is specific. It's derivative with respect to t. This is going to be especially true if you take a class in differential equations, because it's just too difficult to write out all the differentials all the time. So x dot, x double dot, x triple dot, each one of those represents another derivative with respect to time. So it's just a shorthand. The reason I'm bringing it up is because I've talked to several students who have gone on into engineering from this school, and one of the common things they tell me is that the professors use shorthand and expect the students already know it. And it takes a class period or two before somebody recognizes what they're doing. And in college, you might not be able to afford a class period or two. So be familiar that there are other ways to write the derivative. Okay, what I would like you to do now, and this is really for everybody, but I want to make sure everybody who's never had calculus before understands that the people in the room who have had calculus have not done this either, unless they have finished BC. So this is for everybody. And I would encourage you to take a new place in your notes. Everything we've been doing so far has been part of Unit 1.2. We've been in the same unit. But right now, this is generic. You should make an appendix in your notes that is just for calculus. What we're going to talk about today is differential equations. And we're going to take what we've just done and formalize it. The process of finding the antiderivative, what we're doing here, is very informal. It is not what you're going to learn. What you're going to learn in calculus is more formal. It's going to be the integration process. However, we have to solve differential equations. And because of that, what I'm going to need you to do is recognize the vocabulary associated with what we've just done. So this is separate from Unit 1.2. It is a set of notes that you will come back to several different times. We're going to put a bunch of things in here, including the base derivatives that we're going to use in this class, and eventually all of the processes related to taking a differential equation and finding the original equation. So here we go. We're just going to call this kind of a calculus primer. And what we are specifically going to be talking about today is solving a differential equation. Because that's actually what we did when we found the antiderivative and got an equation for the position from the velocity. It's a very simple differential equation, but it's a differential equation nonetheless. Thank you so much. You're the bestest. Now here's the truth. I want to be done teaching so I can go eat that because I am hungry. But I will be patient and eat it later. So we are going to be building a group of differentials, but right now you know of two differentials. These are the two differentials you know. dv dt is a differential, and dx dt is a differential. So when we say that v is dx dt, we are saying that any place where you see v in an equation, it can be replaced with its differential, with a statement about the fact that it is related to time. That's what a differential is. It's giving you a relationship. In this class, we have a small group of differentials that we use repeatedly. These are the most common. The most likely question you will be asked regarding calculus on the AP exam is to create and solve a differential equation. It will sound just like that. The first question will be something like, create a differential equation whose solution could ... the time they will interject right here and say, but do not solve. Meaning they are going to give you points for creating a differential equation. Which sounds maybe more complicated than it actually is. Because there's only, right now in your vocabulary, 2 differentials that you even know about. So any equation that has a in it can become a differential equation. And any equation that has v in it can become a differential equation. So v equals at plus v naught becomes a differential equation the moment you substitute in a differential for v. This is the least likely example of what you'll have to do. The most likely example is you'll start from Newton's law. This is the most likely example, where you'll have to substitute in for a in Newton's law, dv dt. Better than 70% of the times that you were asked to do this, you start with Newton's law. In fact, by the time we make it to November, we will have practiced this so much with Newton's law, you'll be tired of it. But understand, that is the most likely number 1 question. Create a differential equation, you write out Newton's law, and you replace the a part with dv dt. And suddenly, you've already gotten 2 to 3 points on your AP Physics C exam. It's almost always that straightforward. Now, you will very likely see that the next thing is going to be, now solve that equation. We only have one process for doing that. Use is called splitting the differential. And it takes place immediately after you create a differential equation. Splitting a differential is not a particularly hard process, but it is a process, and so I want you to follow the process. Okay? So we had this, dx dt equaled at plus v naught. That's what we just did a few moments ago, so I'm going to stick with it. The process of splitting the differential is pretty simple, but you have to start with a differential. And then you need to be reminded that this, although is a differential and started from delta x and delta t, is still a fraction. The top thing is a number. It's a small displacement. And the bottom thing is also a number. It's a small increment of time. So they still behave like numbers. So step 1 is to multiply by the denominator of the differential. This effectively is splitting the differential. So I'm just multiplying both sides by dt. The next step takes students off guard, but it's just algebra. You need to collect terms. You need to collect terms consistent with the differential. Now I'm saying that. What I'm going to say out loud next, I'm not going to write out because it's a lot of words, but you should. This means you must collect all instances of x on the side with dx, and all instances of t on the side with dt. So if an x appears anywhere, you have to move it over to the side with dx. That's it for today. Remember, what we are trying to do is go backwards, and there's a name for this. And for you purists out there, don't hammer me for this. The antiderivative is the name I want to use. And, I mean, I've been teaching at this school for 17 years, and we've had a variety of calculus teachers in that time. And some of them hate this word. I really don't know where Mr. Bashir falls on the whole scheme of things, and I don't really care. The truth of the matter is, there needs to be a word here to describe doing this backwards. And this word is as good as any. But it's a loaded word, and there's other things actually that we're supposed to say instead. So let me just be very clear. I understand that, but we need a word here. So I'm going to use this word. It just means going backwards. Okay? Now, I'm hoping that most of you realize that if you have this, and you're trying to go backwards, you're trying to do something, and antiderivative is the word I want to use. It's like a box, and it does something to your function, and when you're done, what you have is the antiderivative. It's kind of what we did yesterday. So in this case, I want to take the antiderivative, and I want to take it with respect to x. So most all of you had no trouble, but you're working backwards. So if you'll remember, the last thing we did was subtract something from the exponent. So since we're working backwards, the first thing you should do is add 1 to the exponent. So again, working backwards, the last thing you did was subtract something from the exponent, and right before that we multiplied it by the old exponent. So we will need to divide by the new exponent. But again, the a doesn't go away. The a still stays there. It's still a constant. So this is what you have just done. And I'm trying to find a way to express it. That's what you've done.